Here we continue with electrostatic equilibrium. In this video, we're going to examine the case where we have two spherical conductors connected by a wire. You can see the dimensions of these spheres. This one has a radius of 3r. The one at the bottom here has a radius of r. They each have some amount of charge to start with before we connect them. And the total charge we know to be 4q. Now, when we connect this, what's going to be true of the potential for any part of this system? And the answer is that it will be constant. The entire system will be an equipotential volume. The potential everywhere, big sphere, little sphere, even through the wire, although the wire is negligible, will have the same value of potential. The equation for the potential at the surface of a sphere of radius r is the same as that for the potential V at a distance r from a point charge q. To review, that equation looks like that. That will give us the potential at the surface of a sphere that has an amount of charge q. Using our Part B answer as a guide, as well as the values given in the figure, write two equations, one for Vy and one for Vz. The potential for sphere y, which is the upper one, is going to be k times the amount of charge that y has, which we don't know that amount, but we know that its variable is q sub y, divided by the radius, which is given in our figure as 3r. And Vz, potential for sphere z down here at the bottom, is going to be k times the amount of charge that z has, which again, we don't know the specific amount, we've just assigned it the variable q sub z, divided by its radius, which is merely capital R. And what we want to do is we want to determine the charges qy and qz, noting that the total amount is up here at the top of the screen. The total should be 4q. So how is it divvied up between qy and qz? When these are connected, we've said the potential will be the same everywhere, which means that this expression, k qy over 3r, should be numerically equal to this expression, k qz divided by r. So that means we can cancel some things. The k will cancel, the r will cancel, and what this gives us then is, if I bring the fraction out front, 1/3 of qy is the same amount of charge as qz is. Now I chose easy numbers here. If the total amount of charge on the system is plus 4q, there it is, you can see it in the screen now, right at the top of the page. Doesn't it make sense then that qy would be 3 of those q's and qz will be the 4th? We could write a system of equations and figure that out, but I chose easy numbers, and hopefully you'll see that if you take plus 3q multiplied by 1/3, doesn't that give you just q? When this thing is at equilibrium, electrostatic equilibrium, 3/4 of the charge will be in the top sphere, and only 1/4 of the total charge will be on the surface of the bottom sphere. Suppose now that the system begins with qy being plus 3q and qz being plus 5q, then we connect them with a wire. What's going to happen? Let's figure it out. Before we connect them, Vy is going to be k times qy is 3q, divided by the radius. The radius of y is 3r. And Vz, before we connect these with the wire, is going to be k times its q, which is 5q, divided by its radius, which is just r. This top expression simplifies to kq over r, and Vz has a value of 5kq over r. That means that z has a higher potential than y. So what's going to happen is we're going to get charge, conventional charge, which is positive. Conventional charge is going to flow from z to y. And I chose these numbers to make things easy again, given the radii, this one being 3r and that one being r, basically what's going to happen is y is going to have 3/4 of the charge, and z, when we're at equilibrium, is only going to have 1/4 of the charge. You can see here, when we're all done, y is going to have plus 6q, and z is only going to have 2q. You see the ratio here that's boxed in at the top of the screen? Y is going to have 3 times the charge that z has. Well, that's what's going to happen here. It's just, we started with 3 and 5, so that's 8. So 3/4 of that is going to be 6q for sphere y and 2q for z. And look what's happened. How much did z start with? Z started with 5 and went down to 2. And qy started with 3q and ended up with 6. And so that tells me that charge flowed from z to y, and that's exactly what we said there.